Happy morning, guys. Today we shall discuss chapter 3 electrochemistry as one shot. What are the important contents in electrochemistry? How we have to deal with electrochemistry? How types of questions are asked in electrochemistry? Straight away, let us go to the trend analysis. The electrochemistry is divided into these five parts, that is, electrolytic and molar conductivity numericals, electrochemical cell, Nernst equation, and numericals, electrolysis, and cells and corrosion. Right? These are the five parts of electrochemistry. Electrolytic and molar conductivity numericals will be in the 2 marks as well as in 3 mark as well as in 1 mark. Right? And Nernst equation, this is the first and foremost thing that should come to your mind when you are thinking about electrochemistry. Without that, no question paper is there. And this is most important. This will be asked in 5 marks as well as 3 marks. Right? You can look here. 5 marks as well as 3 marks. You can see here. This is 2018, this is 2019, and this is 20 analysis. D means Delhi, O means outside Delhi. That is not necessary for us. So the point is we have to understand that the electrochemical cell Nernst equation numericals will be there in 5 marks as well as 3 marks. And molar conductivity and electrolytic cell numericals will be in 2 marks, 3 marks, and 1 marks. And electrolysis numericals will be in 3, 2, and 1 marks. Right? 3 marks, 2 marks, and 1 marks. And cells, that will be 2 marks and 1 marks only, because cells is quite a little bit easy, right? 2 marks and 1 marks. And corrosion, so far in the 3 years it has been asked in 1 mark only, right? If the question paper is dead easy, at that time corrosion question may be asked. So we have to give first priority to this chunk, that is electrochemical cell Nernst equation, right? This is the first thing you have to prioritize, and then we have to go for electrolytic and molar conductivity, and then electrolysis, and then electrolysis, and finally we have to give importance to cells, and then at last to corrosion, because it is easiest. Okay, so this is the order we have to follow while revising the electrochemistry. Let us revise the thing. What is electrolytic conduction? The flow of electric current through an electrolytic solution is called electrolytic conduction, right? And electrolyte. These are all basic things which will have a short recap. Electrolyte is a substance that dissociates in solution to produce ions and hence conducts electricity in dissolved molten state. That is called as an electrolyte, right? So you know that this is electrolyte, and the two electrodes are dipped here like this. Okay, right. So what is an electrolyte? It's a substance that dissociate to produce ion. That is electrolyte. And weak electrolyte, strong electrolyte, you should have in mind. Strong electrolyte NaCl, HCl, NaOH. Don't forget. NaCl, HCl, NaOH. Weak electrolytes H2CO3, CH3CO3, CH3COH, HCN, MgCl2. Magnesium chloride, hydrogen cyanide, acetic acid, and carbonic acid, H2CO3. And degree of ionization is extent, up to which extent the ions are in the electrolyte. Ratio of number of ions produced to the total number of molecules in the electrolyte. That is called degree of ionization. And resistance, as you know, resistance, it is to resist to conduct electricity, right? And it is proportional to length and inversely proportional to area. So R is inversely proportional to L by A, or R is equal to rho into L by A, where rho is a resistivity or specific resistance here. And the resistivity that can be given by R is equal to rho into L by A, where rho is a resistivity here. And conductance, that is a reciprocal of resistance. Conductance is a reciprocal of resistance. Upon C is equal to 1 by R, R is equal to rho into L by A, so that it can be written as A into rho by L, or K into A by L. That is kappa. So conductivity, You should remember that C is equal to A by rho L, or C is equal to kappa into A by L. This will help you in solving the numericals. And the unit is Siemens. Conductance unit is Siemens, and 1 Simon is equal to 1 ohm per ohm. And conductivity is a reciprocal of resistivity. Right? Conductance is a reciprocal of resistance, and conductivity is a reciprocal of resistivity, and that can be given by kappa. That is K is equal to C into L by A. K is equal to C into L by A. C is the conductance, L is the area of the cross section, and L is the distance between the two electrodes, and A is the area of the cross section. And this is the unit of conductivity is Siemens per meter. The unit of conductance is Siemens. The unit of conductivity is Siemens per meter, and also explained Siemens per centimeter. So the conductivity depends upon the nature of material, temperature, number of valence electron, and their solvation. And metallic conductance, metallic conductance is electrical conductance in metals that occurs due to the movement of electrons. It depends upon the nature and structure, number of valence electrons, and temperature. Electrolytic conductance or ionic conductance. So this means the electricity conductance due to the ions. Conductance due to the ions present in the solution. It depends upon the nature of electrolyte or inter-ionic attraction, solvation of ions, up to which extent there is dissolved, nature of the solvent and its viscosity, temperature. Right? These are the factors influencing the electrolytic or ionic conductance. And Wheatstone bridge that is used to measure the fourth resistance. But in the case of liquid, in the case of solid, we can connect this with the resistance of the Wheatstone bridge. But in the case of liquid, it is not possible. So for that, cell constant is employed. Conductivity cell is employed there. Conductivity cell is employed. Conductivity cells is connected in the place of fourth resistance, right? And next, the cell constant. Cell constant is a ratio between the electrodes and the cross-sectional area between the electrodes. That is, cell constant is equal to distance between the electrodes and cross-section. The ratio between these two, G is equal to L by A, right? And it depends upon the distance and the area of cross-section. The cell constant depends upon the distance and the area of the cross-section. And basic things we have to brush up now. What is molar conductivity? The conductivity of 1 gram mole of electrolyte in a solution. 1 gram mole of electrolyte. 1 gram mole of electrolyte in a solution. It is denoted by kappa or lambda. Got it? So molar conductivity is the conductivity by 1 gram mole. So what? This molar, that is called 1 gram mole. 1 gram mole. Right? And it is denoted by kappa. And Debye-Heckel-Onsager equation, it is applicable for strong electrolytes. That is lambda is equal to lambda naught minus A root C. This is called Debye-Heckel-Onsager equation that is applicable for strong electrolyte. Right? And lambda naught is limiting molar conductivity, and lambda is molar conductivity. A is a constant and C is a concentration of the solution, right? So Debye-Heckel-Onsager equation, strong electrolyte. And Kohlrausch law of independent migration of ions. So what does this law says? The limiting molar conductivity of an electrolyte, right? The limiting molar conductivity of an electrolyte at infinite dilution. Listen here. The limiting molar conductivity at infinite dilution, that is equal to the sum of contribution from its individual ions. Sum of contribution from its individual ions. Right? Here we can see that is lambda infinity and positive and negative charge divided by the conductivity of the ions. Right? And nu plus and nu minus are the number of cations and anions as per the formula. So this is called rational. That is the molar conductivity at infinite dilution. Limiting molar conductivity at infinite dilution, that is equal to the contributions given by the constituent ions. That is called rational. Right. Then where we are applying this called rational? In the calculation of molar conductivities of weak electrolyte, because you know that for strong electrolyte the graph will be straight line. By extrapolating the graph we can find out the limiting molar conductivity. But in the case of weak electrolyte, the curve will be like this, so that we cannot extrapolate this curve and we cannot find out the limiting molar conductivity for weak electrolyte. Further, the Kohlrausch law is used here. Okay? And also for the calculation of alpha. Alpha in the sense degree of dissociation. So this is most important. Alpha is equal to lambda Cm by lambda naught m, right? And determination of dissociation constant K for weak electrolytes. K is equal to C alpha squared by 1 minus alpha. Alpha, we are substituting the value of alpha here, right? And determination of sparingly soluble salts. Solubility is equal to kappa into 1000 by delta. These are important formulas you have to remember to solve the numericals, right? And here. Got it? Okay. Now, let us have a look over the formulas and we will directly go to the numericals. And current is equal to V by R. Current I is equal to V by R. Resistance is equal to rho into L by A. Conductance is equal to K into A by L. Specific conductivity is equal to C into L by A. That is equal to cell constant divided by resistance. Cell constant is equal to L by A. For strong electrolyte, lambda m is equal to lambda naught m minus A root of C. That is called this is called a Debye-Heckel-Onsager equation. Debye-Heckel-Onsager equation, right? And lambda naught is equal to nu plus into lambda naught plus nu minus into lambda. That is that the conductivity of an electrolyte, that is equal to the contribution of the constituent ions. And degree of dissociation alpha is equal to lambda Cm by lambda naught m. And K, dissociation constant, is equal to C alpha squared by 1 minus alpha. Just now we had seen that can be written as C into del naught m by del naught m into del naught m minus del m. No, actually it is not del, it is lambda. And solubility is equal to K into 1000 by lambda naught m. And superconductors are materials with zero resistance. Limiting molar conductivity. What is limiting molar conductivity? When there is no conductivity, that is called the limiting molar conductivity. When the conductivity approaches zero at some concentration. Ah. Limiting molar conductivity is molar conductivity when the concentration approaches zero. Electrolyte, you know, that is a thing that dissociates over voltage. This will be used in the question where hydrogen and oxygen, sodium and oxygen are competing, chlorine and oxygen are competing in electrolysis. That is, over voltage is the difference between the potential required for the evolution of gas and its standard reduction potential, right? Difference between the potential required for the evolution of the gas and its standard reduction potential, that is called over voltage. So this over voltage you should keep in mind while answering question. This will help. First question. Debye-Heckel-Onsager equation for strong electrolytes. We know that the Debye-Heckel-Onsager equation that they had given here itself, so no need to worry about the Debye-Heckel-Onsager equation for strong electrolytes. Which of the following equality holds? Equality in the sense the lambda is equal to the lambda naught. This is capital lambda. Lambda is equal to lambda naught. So then When C tends to 0, when the concentration is 0, this part will be 0. This part will be 0. So this is our answer here. So here when C tends to infinity, then lambda is equal to lambda. So this is the right option here. Which of the following option will be limiting molar conductivity of acetic acid? If the limiting molar conductivity of sodium acetate is 91 Simon centimeter square per mole. This is the table. That is serial number H plus ion. The limiting molar conductivity is 349.6, sodium ion 50.1, potassium ion 73.5, OH that is 199.1. So among this, what's the question here? Limiting molar conductivity of CH3COH. Okay, they had given the sodium acetate. The limiting molar conductivity of strong and weak electrolytes can be determined by Kohlraasch law. Right? The limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and the cation. Right? So they had given the limiting molar conductivity of sodium acetate as 91 Simon centimeter square per mole. So that is nothing but the conductivity of the acetate ion and the sodium ion, right? And in the tabulation, they had given the value of the conductivity of the sodium ion, right? So by using this formula, that is the conductivity of the sodium acetate, that is equal to the conductivity of the sodium acetate and the sodium ion. So we know the conductivity of sodium acetate and we know the conductivity of sodium ion. From this, we can calculate the conductivity of acetate ion, right? And then here they had given the value of conductivity of H plus ion. So by adding the value of the acetate ion, conductivity value of the acetate ion and the conductivity value of the H plus ion, we can calculate the conductivity of the acetic acid, right? So we found out the conductivity of acetate ion is 40.9 Simon centimeter square per mole and the conductivity of H plus ion is given here. 349.6 Siemens centimeter square per mole. So by adding this by using the Kohlraasch law, we can get the conductivity of acetic acid, that is 390.5 centimeter square per mole. This we can find out in the equation. Yes, 390.5. Okay. Then, which of the statements about solutions of electrolytes is not correct? Conductivity of a solution depends upon the size of ions. Conductivity depends upon the viscosity of solutions. Conductivity does not depend upon the solvation of ions present in the solutions. Conductivity of solution increases with the temperature. Listen here. Here we will make a general mistake that we will forget the word not and we will take the correct option. So it should not be. Read the question carefully. They're asking for the wrong answer here, not the right answer. Okay. So now check out the wrong answer here. Which is the wrong answer here as per your knowledge? Take 5 seconds and check it out. And here the C, the conductivity does not depends upon the solvation of ions present in the solution. It's a wrong thing because if the number of ions increases, the conductivity increases, right? So from this question, we are getting three important points. The conductivity of the solution depends upon the size of the solution. It's a right thing. The conductivity depends upon the viscosity of the solution. It's a very good thing. And the conductivity of the solution increases with temperature. This we know, right? So this is a wrong option here. So here the answer for this question is C, right? Next question. When 0.1 mole of COCl3NH35 is treated with excess of AgNO3 silver nitrate, 0.2 mole of AgCl are obtained. The conductivity solution will correspond to what is the ratio of the electrolyte? Right. Okay. Now here you can look here. When zero point 0.1 mole of COCl3 NH35 was reacted with excess of AgNO3, we get 2.2 moles of AgCl. This is a question, right? What does it mean? 0.2 moles of AgCl means 2 chlorines are here. 0.2 moles of AgCl. So we can understand that there are two chloride ions that are free and not the part of the complex, right? 0.2 moles of AgCl means we can understand that two chloride ions are there. So we can write the structure as one inside among the three chloride ions, one should be inside the complex here. One should be inside the complex and two should be outside the complex so that that two chloride ions can react, right? So let me write it here clearly. That is CuCl3 NH3 5. So here, what would be the what is that? The concentration. What will the exact formula of the compound? That is CuCl NH3 5 times, and outside two chloride ions must be there. The chloride ions which are present outside are responsible for the AgCl uptake, right? AgCl uptake. So the conductivity of the solution will be 1:2 electrolyte. Got it? 1:2 electrolyte. Next, assertion reason type questions. I think you know all these things, and beware of writing the options. Right? If both are right, A. If both are right, but it is not the exact reason. There is no connection between A and B. It is B. If A only is right, and it is C. And if B only is right, it is D. Okay, that's the thing. Here, the conductivity of electrolyte increases with the decrease in concentration. How come decrease in concentration? So it's a wrong thing, right? So just now we had said that the conductivity of electrolyte increases with increase in concentration. So this is a wrong thing. And the number of ions per unit volume decreases on dilution. Yeah, the number of ion per unit volume decreases on dilution, right? So this we can understand by a simple example that we are having some, what is that, some ions here, and if you are adding water here, the distance between the ion increases. That is, the ions will move far away from each other so that the conductivity decreases, right? So the answer is D. The conductivity of an electrolyte decreases with decrease in concentration because the ions per unit volume. This I call per unit volume, particular thing. In a per unit volume, the concentration of ions decreases on dilution. Then next, the molar conductivity for weak electrolytes shows a sharp increase when the electrolytic solution is diluted. For weak electrolytes, the degree of dissociation increases with the dilution of solution. Yes, the molar conductivity for weak electrolytes show a sharp increase when the solution is diluted. That is, in the case of weak electrolytes. Weak electrolytes in the sense they will not dissociate completely. Let me write here. Will not dissociate, 100%, right? So that we call weak electrolyte, right? Then if we add water when it is diluted, the percentage of dissociation increases. The percentage of dissociation increases so that the molar conductivity shows a sharp increase, right? So that the molar conductivity shows a sharp increase. So this is right. And for weak electrolytes, the degree of dissociation increases with the dilution of solution. Yeah, this is also right. Am I right? Because it is not dissociated 100% at once, but we increase the dilution, the conductivity increases. the degree of dissociation. That is, if it is 90% dissociated, I mean, if it is 75% dissociated on dilution, it may 80% dissociate, right? So that both are right thing. So the answer is A. Both are right. Okay. Yes. Weak electrolytes dissociate partially in the concentrated solution. On dilution, their degree of dissociation increases and hence their molar conductivity increases sharply. Next, the electrolytic conduction increases. The electrolytic conduction increases with increase in temperature. Electrolytic conduction increases with increase in temperature. Increase in temperature causes the electronic movement more rapid. Here we can understand that the conductivity or the conduction increases with increase in temperature. This we have seen in an objective, right? Just now, right? And the increase in temperature causes the electronic movement increases. This is not a right thing. So the answer will be C here. As the temperature of the electrolytic solution is increased, the kinetic energy of the ion increases. This results in the increase of electrical conductance of electrolytic solutions. Right? But the electronic movement becomes more rapid. This is not the right thing. Okay? We'll stop here and we'll see the short answer questions in the next chapter.